And then you can close Google Chrome, Linda.
Yeah. Okay. And here I have the presentation of Jaganmoy. Grant, thank you so much.
I'm looking forward to it, Jaganmoy. Sorry, I can't be there.
He's nervous. Now he left.
Ah.
But
okay, I can see the screen, Lindsay. All good. Well done.
Yeah, thank you. And if the power goes off, then we have to start again.
Yes, you do. I'll write a message on the chat if that happens. Okay.
Yeah. I'm going to send a reminder on the chat, Grant.
Okay.
You rest and stay warm. And we'll speak later. Thank you.
Ciao. Ciao, ciao.
I mute for a bit. Hello, we are waiting just a couple of minutes to start, just in case the load shedding hits Wits. And in case the load shedding is going to blank us, please resume yourself in, because we will eventually resume and have the session. Jaganmoy is here, excited. We are all ready to go. Just 2 minutes and then we start. We are back. We are just waiting for projector to warm up. And we put this in presentation. Please let me know if you hear me.
We can. Thanks, Lynn.
Thank you. We are back in business. Projector is there. Okay. We can start. Thank you so much for waiting and for being still online for us. And today I'm introducing Jaganmoy Joda, that is the guest speaker. And I was surprised when I read this bio that actually Jaganmoy was a mud logger. I didn't know
A geologist.
that he was a geologist, logging mud for the oil and gas, natural gas corporation in India. And he did this for 4 years. When eventually he met Professor Axel Hoffman from UJ, and he rescued him, and he brought him back. He brought him to South Africa from India, and eventually started his PhD in 2016, where he started to study the Archean rock record of the Singham Craton of India. Since 2020, he actually joined Wits. He's been snapped from UJ into Wits and is part of the Evolutionary Studies Institute. And as part of his postdoctoral research, he's working on Archean geobiological processes with Professor Pierre Duron. We are very happy to have you here, Jaganmoy. Thank you very much. I hope I can take this window away. Maybe it will go on its own. I don't know what it is. And this is all for you. Thank you.
Okay. Thank you, Linda. And thank you, everyone, for having me here. And sorry for the delay on behalf of Wits. And here we have load shedding schedule for the audience abroad. So yeah, basically, I was a micropaleontologist in India, working for the National Oil and Gas Company of India, which is ONGC. And I was always intrigued by the Archean and the perspectives at how Archean Earth was. So basically, I met Axel in the year 2011, and since then I've known him, and we have been to Barberton many times, and this is where the excitement comes from, basically Barberton. And the Archean of India, the Archean of Singham Craton was something which was introduced later, let's say. So basically today, as you can see, we have a photo which shows you a gate with an axe, which was actually on me throughout my PhD because I was trying to get my PhD done. But in the process, I learned how to navigate through the process of getting into this problem of understanding the Archean and unraveling the mysteries of the Archean. So the first point being said that the Archean is very fragmentary in its rock record itself. And we have barely rocks around in this planet now, which hosts well-preserved rocks from the Archean times. And basically, this is a view of that where you can actually tackle this problem with a door, which is probably at the center, and you're arguing or you're presenting one or couple of arguments in one direction, but you can actually go through this door either ways. You can. It's an open field for research, and it's very exciting. So which we will be presenting from the Singham Craton. And with that in mind, I would like to, I would like to kick off with saying that this talk I dedicate to late Professor Nick Bukes, who was actually instrumental in many of my research perspectives at UJ while I was a PhD student. And much of the research today will be presented from a greenstone succession, where he actually, with Joydeep Mukhopadhyay, documented an age of 3.51 billion years. And that's how I got into the Singham Craton with Axel. So basically, moving on, and as I know that there are many different genres of scientists and audience abroad and also here in this room, I would like to familiarize us with the concept of the Hadean times and how it is and what it is all about. So basically, we are looking at the time period to the left is a general overview of our geologic time scale. So here we have the Hadean time. Thereafter, we have Archean, and following that, we have Proterozoic, Phanerozoic time periods. Now, basically, where I'll be taking you today is shown here in this arrow. where we have the Archean time from the 4 billion years to close to about 2.5 billion years. And much of this will be presented from Singhbum. However, I will mention to you sometimes Australia and South Africa because they host a lot of Archean rocks, which are very well studied and in detail. And this arrow exactly shows us where we are exactly in this time spiral of our Earth's evolution, which is very far deep in our Earth's history. So things are very blurry, and don't expect rocks to be rosy and cozy. And the story is not that straightforward in its first view or one's understanding. So basically, what we know about the Archean is having this picture in our mind, which comes with this view of the Archean Earth, which is quite in absence of ozone because there was no oxygen in the first place. There were plenty of volcanic eruptions all over, and you would have toxic volcanic gases. You can see, you name them, you have them. Then you have the moon, which was much closer to our Earth back then, and plenty of impact events. But more prominently, what you see is that you have presence of primitive oceans, and in parts you will have a prominence of life, which are shown here in stromatolites towards the left-hand side of the slide, and some continents emerging at some point. So this is somehow the overall picture of the Archean Earth. And today, we will understand if Singhbum is a candidate to understand or to know the Archean Earth in a perspective, what we have known so far from the Kapval and the Pilbara Craton of Western Australia. So the aspects of discussion today that I will kind of try to cover will be early magmatism or volcanism, primitive oceans and the presence or traces of early life, and ancient continents. When did they evolve in our Earth's history? So basically, these are the overall anchor points which you will come across, and you will have to make up a story on all of these parameters. So basically, before even going further and discussing that, what I also want to highlight is that the Archean Earth was very different, and probably the Hadean as well. So here is one more argument recently forwarded by our team, which proposed that the Archean Earth and probably the Paleoarchean in particular and the Hadean time was mostly prominently operated by stagnant lid regimes, meaning that plate tectonics was not much of the scenario at that time. And basically how we figured it out is an entire paper, and you are welcome to have a read. But most importantly, the important aspects remain non-varying paleolatitudes, and which were preserved in detrital zircons close to dated about Eoarchean to Hadean times from the Barberton Belt. And this is how we got to know about the plate tectonic regimes at that time. Now, having said that, this is quite exciting about Hadean and Eoarchean time, and why Singhbum is so special, because apparently there's zircons which are of Hadean and Eoarchean times which are reigning in the Singhbum Craton. So basically, these are few of those articles which shows you some evidence of Hadean zircon xenocrysts, which are present in some TTGs, which were dated at 3.4 billion years. Apart from TTGs and Hadean zircon xenocrysts, you will also have zircon in the form of detrital zircon record, which preserves zircons as old as 3.9 to 4.1 billion years in age. So these are a prominent evidence of the early part of our Earth's history being preserved in this craton. Now, having said that, we have to localize and position ourselves. What is this Singhbum and where is it, and where are we exactly looking forward to in the Singhbum craton? So this is an overall view of the Archean craton and worldwide representation of the Archean record on this planet now. So basically, those purple colors are representative of the Archean rocks and where you find them. Most importantly, you see the top box with the purple color again and showing amphibolite and above comes from the North Atlantic craton, where rocks have been metamorphosed and they have seen deformation, and the metamorphic grade here is above amphibolite facies and even touches granulite facies sometimes. So those places, signals or traces of life or something which is very pristine, let's say preservation of rocks are not as pristine as you will encounter in the boxes which are shown here in green, mostly the Kapval craton and also the Pilbara craton. The Kapval is shown here also in arrow because this is where we are now sitting today. And basically, we will visit today the Singhbum Craton, which is shown here in the green arrow, which is in the eastern part of India. So as we have positioned ourselves, so basically what I was encountering during my PhD was a whole lot of confusion and questions regarding, firstly, the mapping of the Singhbum Craton, secondly, the stratigraphic context, and thirdly, geochronology of the Singhbum. So this was a whole lot complicated, and what I will present to you today is much more of a decluttered version of all of these complications, let's say. And we have come up with a consistent framework of the Archean Cratonic evolution. Basically, what you can see on the left is you see the Singhbum Craton, which shows in different colors, different rock types. Basically, the areas which are marked in red are supposed to be making up for iron-bearing rocks or iron formations. However, this is not true. And most of this belongs to supercrustal belts forming Archean greenstone successions or even Cratonic cover successions. You might come across this word or wording called OMG, which is not for oh my God, but this is for older metamorphic rocks. And basically OMTG stands for older metamorphic tonalitic gneisses. Now, these are complicated terminologies which were being used since 1970s, 80s, 90s, and even in 2000. And much of the literature that you will find from the Singhbum will deal with that. But recently, with our work, we have tried to come up with a consistent stratigraphic framework. And every time you will come across this IOG, stands for iron ore group of rocks. It's not only iron formation. There's a whole lot of different suite of rocks, such as mafic, ultramafic komatiites, volcanic rocks, and felsic volcanic rocks, and different sediments associated. If you go to the geochronology part, there will be also aspects of Eastern IOG cluttered with the Western IOG, and where does it sit? So this was the confusion that I dealt with during the first beginning phase of my PhD. And now this is what we present from the Singhbum. More or less what we have here is Paleoarchean to Neoarchean and even younger Proterozoic cover successions. So this is to the left a map of the Singhbum Craton, where you have boxes, of course, which will be discussed in the next slides. But most importantly, the geology is represented in different colors. Now, the central part of the Singhbum is made up of largely TTGs and granitoids, and even granites, which are more potassic in composition, much younger in age, largely represented by pink-colored areas. However, the green slivers that you see are greenstones, which will be coined or will be assigned to the Badam Pahar group of rocks. And towards the west, if you see this big red rectangle box, that is the Western iron ore group, much younger in time period compared to the Paleoarchean greenstones. So basically, these are the few geologic markers which will be used, and the framework of the geology is shown here in this stratigraphic column, a simplified one, rather to make you understand how the geology is actually there. Much of the greenstones are interleaved with TTGs of the Singhbum granitoid complex, which we assign to. The older pre-tectonic suite is known as the Champua suite, which, however, the youngest one is marked by the potassic ones, which are shown here in pink color, of the Mayurbhanj suite. And this also is important because the Mayurbhanj granite was in place at 3 billion years and results in civilization of the Craton. After that, we have deposition and emplacement or more younger volcanic rocks, which is shown here higher up in the column. So this is overall understanding and will fit in the puzzle later on. And I just wanted to make you understand the geology so that we are familiar with it in some parts. Now, having said that, we will travel across the Craton from the south to the southeast and move to the north and follow up to the western part. So we will cover a lot of this Craton through today's presentation. But for the first part of our presentation, we will largely focus on the Badam Pahar group, which is mostly the Paleoarchean greenstone successions. And for students or for researchers here in South Africa, you will find very much similar geology from the Barberton greenstone in Southern Africa. Now, this is the Daitari Greenstone Belt, and also where I spend much of my time mapping the central portion largely of the greenstone succession. To the right is a map which is shown, and where Axel and I, we spend a lot of time in this area mapping the greenstone. So to the northern part of this geologic map, you will see these TTGs, which are intrusive, and they have a contact which is shown here in the northern part with the older mafic, ultramafic komatiite successions, which are marked in green. So they are the oldest suite of rock you will encounter in these greenstones. Above that, we have a felsic volcanic unit dated at 3.51 and will be discussed. And higher up in the stratigraphy, you have turbidites and more sediments, which are of chert and banded iron formation, which are shown here in blue and red colored patches in this map. And following up, we have more mafic, ultramafic volcanic rocks higher up in the stratigraphy. And above this, we have an unconformity, which is marked by this deposition of sandstones shown in yellow of the Mahagiri quartzite, which has a maximum depositional age of 3 billion years or so. And this greenstone belt will be discussed in detail because we know a lot on the geology and the geochronology and geobiological aspects of this. Otherwise, we will deal with the other greenstones briefly here. So overall, the Badampahar group, which is shown here to the left, is shown in this stratigraphic column. Here you have TTGs, which are intrusive towards the lowermost part of the greenstone, where you have mafic, ultramafic, and komatiite bearing basaltic rocks. So these are the typical rocks that you will come across when you visit Daitari. You will come across spinifex textured komatiites, pillow basalts, which are huge and gigantic. You may hardly see the hammer, which is popping small over there. So these are massive pillow basalts, which are undeformed, barely deformed. And above that, we have a succession of felsic volcanic units, which is forming the Talpada formation close to 1.5 kilometers or so. And above that, we have turbidites close to 500 meters of the Sindhurimundi formation. And then above that, we have iron formation and cherts, which are shown here in this photo. And following that, we have mafic volcanic rocks. So this is the geology. And how do we know that these greenstones are older than 3.51? As I've mentioned, these volcanic rocks were dated already in 2007. And as I've mentioned already earlier, that Joydeep Mukhopadhyay and Nick Dukas involved dated one unit of this felsic volcanic horizon, which yielded them uranium-lead zircon age of 3.51 billion years. Now that got us excited. And for us, it was almost like a nightmare to compare all this geology and to do strict mapping of this area. However, what we found out is that these outcrops are well exposed in many parts. And you will come across outcrops like that to the right, which are felsic volcanic agglomerates, which are in the form of bombs and blocks of rocks embedded in tuficeous matrix. Now, those rocks were dated at 3.51 billion years and also are dating at different units in the stratigraphy. We were also able to encounter same identical ages, meaning that this volcanism was of the same time frame. Now, meaning also, if I go back to the slide, is that the rocks, which are komatiites and basalts, are older than 3.51 in the lower part of the stratigraphy. And higher up, we have younger sediments and volcanic rocks associated. So that's the overall understanding. Now, other part of my PhD was to unravel the mysteries on the geobiology, largely talking about early life and how was there any life in the Singhbum, because there's been talks and debates about early life from the Kapval Craton, from the Pilbara Craton. And I wanted to see if, how about these carbonaceous rich rocks? How about cherts, which are organic rich, and shales, which are organic rich? So that was the motivation for me to go and hunt for these rocks and do carbon isotope studies. Basically, what you see is, again, the stratigraphy to the left, and you see cherts and shales, which are represented in different dots, cherts by blue and shales by gray dots. So if you see the TUC variation through the stratigraphy, you will encounter that the highest total organic carbon content of the cherts amounts up to 1 weight percentage, which is quite significant. However, if you note this total organic carbon content of shales, they are close to about 5 weight percentage. That's immense. And we are talking about shales, which are of Paleoarginine age, and that has nowhere been reported so far. And apart from that, what we see in the stratigraphy record is that there is a variation in the carbon isotopic composition. Towards the bottommost part, we have carbon isotopes ranging from -13 to -30 sometimes. However, if we move higher up in the stratigraphy, we have values close to -34, and shales showing or clustered close to -30, -25. Now, what does this mean? To the right is a plot showing carbon isotope versus total organic carbon content. And here you see shales and cherts. And what is important to highlight here is that these rocks have seen or undergone green schist phases of metamorphism, meaning that there was some panitic isotopic fractionation effect, meaning some pristine signals have been obliterated, and now what you see is not pristine anymore. So basically, we would have heavier values instead of the much lighter values. So basically, all the values which you see towards the right should have been shifted per 5 per mil to the left, meaning that what we have close to -35 should be shifted to -30 and so forth. So basically, if we take into account a biogenic versus biogenic carbon and where we sit, if we take into account mantle carbon, which sits from -10 to plus 5 or 0 per mil, here all the carbon isotopic composition suggests that these are all probably biogenic in origin. And here are some highlighted microbes that you can vision of, which could have been involved in fixing the carbon. It could be methanogens, methanotropes, anoxygenic photosynthesizers, and many others. So basically, that is the story from carbon isotopes. And if you have not enough dose of carbon isotopes, I present to you nitrogen isotopes, which is again an exciting isotope of which was something which we thought that would be interesting to see if there were microbes which were able to fix nitrogen in the Archean record of the Singbum. So basically, to the left is a plot of many different dots, and the real thing that you will encounter are these rectangle boxes. So basically, to the topmost part, you will see the shales from Daitari, which had the total organic carbon content of 5 weight percentage, close to about, and some close to 1 weight percentage, and they were all analyzed from their bulk kerogen extract, bulk nitrogen values, and kerogen extract nitrogen composition. What we see is that both bulk versus kerogen, they track well to each other, meaning that they have close isotopic composition or variation, and which is significantly important to identify any fixation, any nitrogen fixation processes during the Archean. Basically, what I'm trying to say here is that there were previous research conducted from the Pilbara and the Kapval ketons, which suggested that at delta 15 nitrogen composition close to about 0 or plus minus of 2 per mil within an error, you'll have that blue field, which is mostly for molybdenum nitrogenase, which was used by these nitrogen fixing bacteria as a cofactor. Now, having that in mind, we see all of those values mostly within that field, and some, if we take into account again the metamorphism effect, all the heavier values should shift down. So basically, we are talking about nitrogen being fixed in the Singbum craton at around 3.5 billion years or so. So this is quite remarkable. And what we have at the bottom part is, again, there's a new study from the Buckreef Church from Southern Africa, where they are arguing about nitrogen being fixed in the presence of iron. So even some of those values which you see have a positive delta 15 nitrogen signal would be well within this framework of nitrogen being fixed as we take into account the Barberton study. So basically, what I'm trying to overall summarize here from nitrogen perspective is that we have again filled in a huge gap from nitrogen isotopes and carbon isotopes, mostly here showing you nitrogen data set, where Singbum data is fitting at 3.5 billion years, and the only oldest data point what we had was from Isua at 3.7 billion years or so. However, we are not sure of how the nitrogen was fixed there because the rocks are of high metamorphic grade, and we cannot say by certainty that these were biological or abiological in origin. Now, moving on from that, I was also curious to know the microfossils and microbial life in terms of their morphology. So this is one of that kind of microfossil which I wanted to show you. These are all made up of carbonaceous material, which we have investigated under the microscope, and also Raman spectroscopy provided some carbon signals. And here you see these are lensoidal to spheroidal shape nature of these microbial structures, which has a tapered edges. And a recent study from Pilbara craton suggested that those tail-like appendages were used by those microbes to for active motility or movement. So these are also the first reporting of such microbial structures from the Singbum craton. Now, overall, if I were to understand the geology of this greenstone succession in detail, and if I were to see this, it would be like this. You would have a Paleoarchean greenstone succession. Mostly, much of the mafic, ultramafic volcanic eruption happened or took place under submarine settings. So it's very important to note. And however, we have some phases of felsic volcanic eruptions shown here in this figure to the right. At times, this felsic volcanic eruption may have acted subaerially, meaning above the water levels, and also giving rise to further erosion and products of felsic volcanic edifice in the resulting in turbidites, as you see in the stratigraphy of the Sindhu-Rimundi clastic sequence. Higher up, we have chemical sequence of sediments such as banded iron formation and cherts, which took place when there was no volcanism or break in volcanic activity. And above that, we have another sequence of marine volcanism. So this being said, this is very important and one of the key slides, because this is highlighting the Paleoarchean greenstone geology, which means that we see volcanism mostly predominantly under subaquatic settings, also sediments depositing in those conditions, which will be different to the other sequence of rocks which will be discussed. Now, apart from the dietary belt, as I've highlighted that there was a different greenstone sequence exposed in the southeastern part, I'll not go into detail, but what we see are greenstones, which are marked in green, intruded by granites of different ages, and also sandstones, which are shown here in yellow. Now, with our recent study, what we have also seen from the field is that this greenstone geology may not have been best preserved because it has ultramafic, mafic volcanic rocks, which are highly altered, as you can see in this photograph. But nevertheless, they preserve ultramafic, mafic, and volcanic suite of rocks with banded cherts, close to the same association that we have been noticing so far from Daitari. And overall, here we have again association of a sandstone unit, which we dated at 3.3 billion years. And to our understanding, these greenstones below or interleaved with these sandstones are older than 3.3 billion years, meaning again Paleoarchean greenstone succession. Now, moving from the southeastern part of the Singbum, when we travel to the northern part, and I will just again highlight the upper part of the northern greenstone, which is also known as the Gorumoisani greenstone belt here. And these are the exposed greenstones over there, which are, as you can see, intruded by different suite of TTGs and granites of different ages, ranging from 3.53 to 3 billion years, where the 3 billion year being marked by the pink colored granites of the Mayurban suite. Now, basically what we encounter in this greenstone succession in the northern part is also remarkably similar to what we have noticed so far from the greenstones of the Daitari greenstone belt. What we see here are pilobasalts, kumatites, and also banded cherts and iron formation, together with minor interlayered felsic volcanic rocks. And until our data from the Gorumoisani area, this greenstone was questionable, and people were questioning of its age, whether it's Paleoarchean, Meso, or Neoarchean in age. However, a felsic volcanic unit that we dated in this greenstone provided ages almost identical to the felsic volcanic age of Daitari greenstone belt, which are shown here close to about 3.51 billion years in age. Now, having said that, moving on to our other finding from the Singhum, and what we corroborated from the other cratons here is mostly in terms of felsic volcanism, which is noted at 3.55 billion years. So this to the left is the Singhum geology, and also from Gorumoisani. I did not have space to accommodate the stratigraphy there. But overall, we have felsic volcanism at 3.51 in Singhum within the greenstone geology that you will encounter. And if you were to study the greenstones from Barberton, you were to study Thiesproit and Sandsproit formations where there are felsic volcanic events noted at 3.51. They are also of the same age. And if you visit the Nongwini greenstone belt in the Kapval Craton, you have the Togo Cree formation, which has volcanic rocks dated at 3.53 to 3.51 billion years. Now, these are remarkably similar volcanic events in different places. And now if you visit the Pilbara Craton, which is shown here to the right, in the Kontoruna group, probably I should use the Kontoruna group, as also felsic volcanic rocks, which are dated at 3.51 billion years. So these are remarkable felsic volcanic events dated at 3.51 billion years. And we were also lucky to have this study and some news popped up with our research in recent times. So basically, what I'm trying to also highlight here is that the greenstones are not alone here. They are also together with concomitant phases of felsic magmatic events. What you see here are 2.53 billion year old banded gneisses, which were dated at 3.53, almost the same age as of the greenstones. And they were erupting almost at the same time. However, we also have younger phases of TTGs in place and even much younger at 3.35. And there are other events. So if you were to study and if you're interested to look at the Singhbum TTGs and granites, this is a compilation of the different TTGs and granites which have been compiled in this figure here. So there are trondhjemites, tonalites, granodiorites and monzogranites, and yeah. So the important fact remains that the younger granites are more potassic in nature, whereas the older TTGs are more sodic in composition. And as I've highlighted already, that some TTGs do not only host their crystallization age, but also they have reworked some of the older component in the form of Hadean xenocryst, which are dated at 4.2 billion years. Now, this is a hafnium dataset compilation from the Singhbum. As we were also interested in the hafnium, you see different dimensions of research. So basically what we found out in this compilation is that different other workers have found some Hadean and Eoarchean dataset, whereas we have some dataset from 3.5 onwards. And what we see is that we have this Hadean mafic protocrust moving away in terms of hafnium initial composition. And at 3.5 billion years or so, we have this epsilon hafnium close to about chondritic values, mostly close to 0. So this is a huge shift, and which is also noted in hafnium isotopic composition from the Pilbara and the Kapval cratons. Now, moving on, and what we have noted so far is all the Paleoarchean greenstone successions, so which are marked here in rectangle boxes. And as I've shown to you, that the greenstone geologies are ranging from 3.55 in terms of the tetrahedral zircons. We have older record, and we have granite greenstones associated with Paleoarchean volcanosedimentary successions, which are preserved in the south, southeast, and northeastern part, where we have greenstone successions mostly featured with lower greenish phases of metamorphism. And after that, we will be entering into a new era of geology into discussing the Meso to Neoarchean time period. So basically here we are talking about geology from the western part of the Singhbum and also some parts of the Simplipal, which is shown here. So this area is well known as the Koira group, and this is the Simplipal group, where these rocks are very different to what we have seen so far. So they are largely in the western part of the Singhbum Craton, preserved as cratonic cover sequence. And what you see here are basement rocks. And above the basement rocks, you have a paleosol, which is dated at 3.0 or so billion years. And we have sandstones, which are shown here in the map. And the granites are forming the basement. Above that, we have sandstones and volcanic rocks, much similar to the geology that you will encounter in the Pongola area. And above that, we have iron formations and shales, which are manganese bearing. So this is quite remarkable in geology, because there's nothing of this kind in the Paleoarchean times. So now, having said that, what do you encounter if you were to visit this area? So you will see sandstones plenty everywhere. You will have shales with manganese and iron formations. You will have volcanic rocks, largely vesicular volcanism, vesicular filled basalts, or volcanism suggesting subaerial settings, meaning that there were not much of volcanism involved under subaquatic settings. So we have largely subaerial lava flows or continental flood basalts, and which is very different to the Paleoarchean greenstones that you have seen so far. And here we also have some stromatolites which are preserved, which is shown here in this photo. And we have iron formations with manganese reserves. So basically, this is again, we debunk one of the oldest claims on the western part of the Singhbum Craton, where different workers from different time periods have suggested that that's a Paleoarchean greenstone succession. However, the age data and the geochronology does not agree with their claims. So basically, the sandstones here are dated at 3 billion years, and some sandstones which are interlayered within the shales and iron formations above are showing you the tetrahedral zircon peaks at 2.7 to 2.6 billion years. So these are again suggestive of the fact that the maximum deposition of these sediments was much younger than that. So having that in mind, Again, geobiology of the western part of the Singhbum Craton, which is quite remarkable. Here you have pavements of ripple bedded sandstones. And here you have some microbially induced sedimentary structures. And on the right-hand side, you will have some microfossils, which was reported in the year 2000 by Maite et al. So these are cocoid-shaped microbes, which are largely made up of carbonaceous material, and they will be they are shown to be preserved in some chert units within this cratonic cover succession. Now, what you will encounter there are these huge mines, largely mining iron and also manganese in places. And this has been quite an event of mining since the independence of India. And actually, this is quite remarkable to note that India is at the 4th position. I know that some of you are economically interested and vested in that, so I wanted to include some of this economic geology slides and the economic prospects of the Singhbum Craton. So basically, India is now at 5.5 and today I checked up with the Indian Bureau of Mines. Overall, the estimated reserves of iron is close to 25 billion tons, if I'm not wrong. And India was at position 4 by producing that much of iron in the year 2021. However, what I'm here to highlight is the aspect that the Singhbum Craton, which is situated in the states of Orissa and Jharkhand, is largely accounting for 63% of the total iron production of the country, which is enormous. So basically, this craton is also huge in terms of its iron ore reserves. And the economic geology of this craton is well beyond imagination. But it's a pity that so far, nobody highlighted this craton in the world map of iron ore reserves or iron bearing formations. So what we have so far is a map of the iron formations overall. And today we would like to highlight that the Singhbum iron formations, which are also largely instrumental for the iron reserves in the Singhbum Craton, could have been well for the iron formations dating back to 3.3 billion years or 3.5 in places, and the Meso to Neo-Archean iron formations that you have seen so far. So this is where we put Singhbum, and in the map of the global context, it was missing so far. So here we have included that piece of information in terms of iron formation and iron bearing reserves. So with that, I would like to summarize the geology and the context of the Singhbum Craton. So as I've already highlighted that the Paleoarchean greenstones are very different to the Meso or the Neo-Archean cover successions. So this overall is a timeline of the geologic evolution of the Singhbum Craton. What we have are Paleoarchean greenstones, mostly known as the Badampahar group, as you have seen. So far, you have seen that the Badampahar group was largely made up of volcanic rocks, which erupted under submarine settings with minor phases of felsic volcanism and concomitant phases of TTG emplacement. And with that, we have sediments deposition, which are roughly banded iron formation and banded cherts. And at 3.3 billion years or so, we have sandstones forming the Dosra Pahar group, which is roughly the same age as you will encounter in the Moody's group of the Barberton greenstone geology. However, here we also have TPGs and granitoids emplacing at different time periods. Roughly at around 3 billion years or so, we have the heralding of the craton stabilization marked by the emplacement of the Mayurbhanj granite, and which acts as the basement for the cover sequence rocks of the Koira group. So basically, the Koira is largely made up of sandstones and conglomerates with volcanism, mostly showing continental flood volcanism or style of volcanism, which is very different to volcanism, what is noted from the Paleoarchean times. And also you have large dike swarms dated at close to about 2.7 billion years or so. And also emplacement of different different felsic components. Now, after that, what we know and what we have gathered so far is, if I were right and if our objectives were correct, we understood some parts of the early magmatism from the Singhbum geology. And these are some boxes which I would like to fill. Basically, primitive oceans and traces of early life, which are preserved in the form of banded cherts and banded iron formation, which is also filled, and also ancient continents, which probably heralded afterwards in the Singhbum geology from the time period of 3 billion years or so. However, there's much more work to be done. And in the direction of that, what we are trying to understand is the Singhbum craton connection to Kabwal and the Pilbara cratons. We are also interested, I'm sorry for that. We are also interested in the primordial gases evolution from the Singhbum craton, if we were lucky. And also the other part would be to study the impact events. So these are the few other dimensions or directions of research that we are undertaking right now, and we are trying to fill more and more gaps. And everybody is welcome to join our venture and vision here to improve on the geology of the Singhbum craton. Overall, what I want to take from here for young students and researchers who are trying to understand, search for extraterrestrial intelligence or life forms elsewhere, what I want to introspect is that we want to have more and more geology and basic fundamental geology done on planet Earth. And only then we can have more and more understanding or better understanding of, let's say, life elsewhere, which is great because we are proceeding and marking way ahead in that dimension. And a recent research has highlighted the significance of such discoveries of phosphates from the moon of Saturn, Enceladus. So basically what I'm trying to say here is that we need to have more and more Singhbums, Kabwals, and Pilbara cratons where the rocks are best preserved, and there you can see remarkable geology to be studied, and where you will be able to do more and more research for future generations coming beyond in time. And let's celebrate. I think the people of Singhbum are also celebrating with the fact that there was some occasion which I'm not aware of, but probably this is towards the end of it, and I want you all to have some beers and fun time. And with that, I would like to acknowledge the sponsors and all the people who have helped me unraveling the mysteries of the Singhbum craton throughout this period of my journey in the Singhbum. Thank you so much.
Thank you very much, Jaganmoy. It was a long work for your PhD, a lot of mapping.
Yeah, a lot of different kinds of work.
Is there any questions?
Yes, Roger.
Great talk, Joe.
Thank you, Roger.
Could you go back to the slide with summary slide?
Where? Here? No, sorry. Beyond. Here?
Yeah. And I mean, you said there that the next phase is looking at the Kabwal, Pilbara, Singhbum correlation. But you look at that and you built the case for the sort of the early Archean correlations. But looking then at what has happened, the Wits comes in just after 2.96 and is primarily acidic plastics.
Yeah.
You've got a sandstone conglomerate succession.
Yeah.
It goes down to 2.8, which is now the age Pentastal volcans.
Yeah. Yeah.
So how what are you thinking in terms of this? Did we have one craton sitting there that is now split into three pieces? Sometime maybe by 2.7 goes its way. So, and the second part of the question is there a sort of a Transvaal supergroup correlation in the Indian context? Or is there nothing equivalent to what we see in Transvaal? So these things might be together up until about 2.6 or so, and then go their separate ways.
Yeah, well, thank you so much, Roger, for this question. If I were to go back and show you something, I get a lot of this question and many people confused. Oh, is that in the right direction? Maybe. So basically, with that, I would like to highlight the fact that this was also one of our key findings, like one of the observations, not findings, but that the felsic volcanic event at 3.5 was more or less noted from all these different cratons, which is quite remarkable. Now, we are no way saying that they were together, as in piece of one continental landmass, or in that time period they were together. But probably geologic processes operated similar in all of these cratons if they were geographically isolated, which could be one case. If they were together or not, much of the paleomagnetic study has to be done, in which we have not gone far beyond the efforts of finding well-preserved paleomagnetic observations. So I'm not sure of putting them together and bringing like a one continent story. However, what you asked me would be going back, and basically here would be the, if I Yeah. So basically here would be the Paleosol in the Singhbum Craton, and the sandstones here are dated at 3 billion years or so. But importantly, we have detrital zircon ages noted at 2.9, just like the Witwatersrand sandstone age. But also there are also younger detrital zircon population. So what we note here is that probably this sandstone is round about the same age of the Wits Basin, within an error of some million years, but we are not sure. Now, coming about Transvaal supergroup, which would shoot up above the stratigraphic column here, because this is more like the Neoarchean stuff. I'm really not sure if there is a equivalent of that, but actually we have, I cannot show you the other sequence of rocks actually here, or maybe I can go back and show you something. Yeah. So basically here there is a group of volcanosedimentary sequence of rocks in the northern part of the Singhbum, which is well known as the Dhanjori group. And there are some detrital zircon age data. Now there are more detrital zircon age data set which are coming up. And we are thinking that possibly this is one of those probably equivalent to the Transvaal supergroup. But we do not see much of the same geologic units, which may have been eroded or some way not being the same anymore. But yeah, so probably Dhanjori is one candidate for the Transvaal, but so far much more research has to be done. So yeah, I don't know if that answers your question. Okay. Oh, it's a big question. It's a huge question.
From Sharat, shall I read?
Yeah. You can read, but maybe
So
this will make the others sleep, right? It's a huge question. You mentioned the Simlipal Basin containing volcanics and quartzites which unconformably overlie the Paleoarchean greenstone with an unconformity around 3 billion years. But Mishra et al. Suggested that the granites were intrusive into the Simlipal, which gave an age of the impact structure as between 3.2 and 3. Any comments? Perhaps the granite Are there any detrital Okay. Yes. Thank you, Sharat, for this long question, if you're listening. Yeah, so basically, okay, so the first thing is that these granites are not intrusive. They are actually forming the basement for this Simlipal group of rocks. And basically, I have to go back to the question.
Oh, sorry.
It's a massive question. It's a mammoth. Okay. But Mishra et al. Suggested that the Mayurbhanj was intrusive. So yeah, so basically it's not intrusive, which gave an age. So, but and again, the Simlipal is not an impact structure anyway. So that's been done. So people have been trying to argue for the fact that the Simlipal, which is sitting here, is an impact structure, and nowhere from our field evidence is that an impact structure. Perhaps the granite dated by Mishra is the Mayurbhanj granite. Yeah, that's true. That's 3 billion years, and that's where the sediments are sitting above these granites. So basically, these sediments with the volcanics are sitting above the granites, and they are the granites are not at all intrusive. Are there any detrital zircon? Oh yes. So basically, the detrital zircon record I have presented from the it goes back to a paper which I present at the beginning of the talk, and I have to roll back. So where it was raining Hedian and zircon. Yeah, here. So basically, this is the paper. If you are welcome to ask me, or you can go to Precambrian Research and look up for this article where they suggest the age of the Simlipal group is close to about 3 billion years with the youngest population of zircon, and where they also note some Hedian zircon grains. So basically, this is suggesting that the Simlipal got deposited after the emplacement of the Mayurbhanj granite, and not that the Mayurbhanj is intrusive. So I hope that is Simlipal is proven as an impact published in blah, blah, blah. Okay. Well, okay, I have to read up that probably, maybe, yes. I'm not sure, but yes, maybe. But overall, for the understanding that we are growing with the body of research in Singhbum so far, Sharat, that is not the case. Sorry.
Is there a question from the audience? Please, Chris.
Hey, hi.
So come back to your story about carbon isotopes?
Okay, should I go back to the slide?
Well, no, it's just a question.
Okay.
He suggested that metamorphism should increase the ratio of isotopically heavy carbon by about 5 mol.
Yeah, so
Is that constant?
it's an experimental study, and it was done by probably Sept et al. 2006-17, if I remember them. There are many other studies. It's not only one study. There's many others, but I like to follow Sept's work, and they argued for carbon isotopic composition to have shifted because of the effect of thermal degradation, meaning that if you would have pristine values, which are more negative in composition, you can cook the carbon and then bring it to more heavier values. And if you cook the carbon entirely, it would become a graphite or diamond, where you would have no trace of any biological, let's say, remains in terms of isotopic composition.
Okay, so your point is isotopically light signal has to be lighter than
As isotopically lighter values are indicative or suggestive of biological fractionation.
And
Yeah.
would metamorphism affect the rocks in a constant manner? Would you expect?
Well, yeah, these rocks have seen so much of deformation and metamorphism. Like there are so many events, as you have seen the greenstones, which have been intruded by multiple phases or episodes of TTGs and granite emplacement. So there's like events which we don't know how much and how long they were. So we are not really certain how long these events were, but probably several millions of years. And basically, yeah, I can't answer that exactly within like a strict time frame of like metamorphism, how much and when it got cooked. But over the Earth's history, there have been many phases of emplacement of, or even metamorphic events, which actually this rock suffered. So yeah, they have suffered a lot. They've gone through a lot.
Okay, I have to say thank you to Jaganmoy and to the audience for being here today. And if there is any question, you can always interact with Jaganmoy over a beer or so.
Oh yes, sure.
And thank everybody. Thanks in particular John Ankles and CCIC for supporting events with our drinks. And I will have to remind everybody to be here next week at 1600, where there is going to be Bruce Kiersgaard, sorry for killing this name, and George Reed, that they are going to speak on the economic evaluation of kimberlites. So it's going to be an economic geology talk. And thank you everybody, and see you next week. Bye.
Thank you. Thank you very much, everyone. Thank you, Linda.
No, thanks to you.
Thank you. Hope it was honest.